In this problem, we're going to learn how to calculate electrical cost savings by replacing an old inefficient pump with a newer, more efficient pump. Well, let's go to the board and see how to work this problem. Well, the problem reads, a 6-year-old pump motor is to be replaced. The new motor, just like the old one, would run 75% of the time. Both existing and replacement motors would operate at 100 output horsepower. The existing motor efficiency is 86%, while the replacement motor would be guaranteed at 94% efficiency. Electricity currently averages $0.078 per kilowatt hour. Calculate the energy cost savings per year to the nearest dollar and assume 365 days in a year if the existing pump is replaced with the new pump. And we're to neglect any consideration of or impact on demand charges or interest on capital. Well, there's a lot going on in this problem, and there's a lot of numbers in this problem, so we're going to do what we always do, and we're going to pull those numbers with the units out by writing down our known and our unknown information. They want us to find or to calculate the cost savings per year. So that's our target. We're looking for dollars per year saved. Well, they told us that this motor and the pump is going to run 75% of the time. So our run time is 75% of the 365 days. They also told us that we're going to be operating at 100 output horsepower. Now that's important. Because the motors are not 100% efficient, there's going to be some losses. So to operate at 100 output horsepower, we need to put more horsepower in. And we'll use the efficiency to calculate how much more horsepower we need to get that 100 output horsepower. So our output horsepower is 100. And then they tell us that the old pump is 86% efficient, so we write that down. And the new pump is guaranteed to be 94% efficient, so we write that down. Well, we're going to use our brake horsepower formula, which states brake horsepower is equal to the power to the motor times motor efficiency. We're going to be looking for this power to the motor, because if we can find how much power we have to give to the motor, through the electrical company powering that motor to get 100 horsepower out, we can take that difference, and based on the difference in horsepower required from the old pump to the new pump, that's how we're going to calculate our annual cost savings. So we need to rearrange this formula to solve for power to the motor. So to do that, we use our diagonal rule, and we're going to divide both sides by the motor efficiency. So when we rearrange this formula to solve for power to the motor, it ends up looking like this. Our brake horsepower divided by motor efficiency is equal to power to the motor. Well, our brake horsepower in this case is that 100 or 100 output horsepower. So what we're going to do is we're going to use this formula, and we're going to solve for two numbers. We're going to solve for the power to the motor with our old motor, the 86% efficient motor, and then we're going to calculate the horsepower required for the new motor, and we'll take the difference. So in the first case, we're going to do the newer motor, so 100 horsepower divided by 0.94, which is the efficiency. And when we work with percents, for most wastewater problems, we want to use the decimal form. So our 100 horsepower divided by the 0.94 gives us 106.38 horsepower. So we need to supply 106.38 horsepower in order to get that 100 horsepower out. Well, the old motor requires 116.28 horsepower because it's less efficient. So the difference between these two numbers, this 106 and 116 horsepower, that difference is going to be where our savings is going to be made. So we're going to take the 116.28 horsepower and subtract the 106.38 horsepower. And when we do that, we get 9.9 horsepower. So that's our savings. Well, now we need to convert that horsepower savings into dollars per year savings. So starting with our 9.9 horsepower, we're first going to convert that to kilowatts. And we use the equivalent that says 1 horsepower is equivalent to 0.746 kilowatts. And that gets our horsepower into kilowatts. Well, then we're going to use our cost per kilowatt hour. So in the problem, they told us that 1 kilowatt hour cost $0.0780. So we put that in there. And we're looking for this cost per year. So 1 year has 365 days and there's 24 hours in each day. So when we do this unit conversion, the units cancel out and we're left with dollars per year. So we took our horsepower, multiplied it by our conversion to get us into kilowatts. We multiplied it by our cost per kilowatt hour, and we multiplied it by the hours per year that we operate this pump. But look back in our known information. It says our runtime is 75%. So we don't want to forget that this pump and motor, they're only running 75% of the time. So we have to add that in down here. Well, now that we have this problem set up, we simply multiply across everything on the top and we'll find our answer. And in this case, we're going to be saving $3,785 per year. And that, my friend, is how this problem is solved.